So welcome everyone to day 2 of GSUK Virtual Conference 2025. I'm very pleased to introduce Sarab Pandey from BMC this morning. He's going to take all your stress away for taming page splits. So this is something that I know I've seen lots of pain points around, so eager to watch this one. Please ask the questions in the chat as we go along, and I'll take pauses and speak out the questions, and there'll be a little time at the end just to ask any further questions. So please use the chat for that, and enjoy. Over to you, Sarab.
Thanks a lot, Colin, and welcome everyone. Good morning to all. So already been introduced, so I'll directly, go to the topic. So we are going to talk about the page splits, basically index page splits, and how to bring down the stress for the DBAs. Although the stress is a part of life for a DBA, and and every vendor and IBM is trying pretty hard to bring down that stress. So this is one of the topics which I think uh, is an interesting topic because something have been changed and enhanced in 13 DB2, and I thought it's worth talking about it and compare it and talking a bit about the page splits. So that is also a very interesting topic. So let's get started. And if you have any questions, please drop in the chat or let Colin know. We can discuss that. So this is a basic hierarchy of DB2 object structure. You have database, which includes, the physical table space and index spaces, which are basically provisioned over storage groups, different storage groups and volumes, and there are different multiple things. This picture I just thought to put it here, just to freshen up our memories. Then we directly go to understanding different types of indexes. I'm not going to dig deeper into index types and everything about it, just to refresh our memories. So unique index, we all know, it ensures that not two rows are identical and the values are stored in a table are unique. And but if you see the way indexes are connected to the rows is not in order, so it's not very intelligent way, but still it makes sure that you do not have duplicate rows in the table. On the other hand, by the way, these pictures are from IBM Redbooks. You might have already seen it. Other hand, you have clustering indexes. So the clustering index basically means that the index enforces the physical order in the table rows based on the order in the index, so that there is a one-on-one mapping and from the index keys to the rows, and it becomes easier to fetch the rows. So it's like forcing the primary sorting mechanism on actual data. So that is the clustering index, and we all have seen it in our lives and the importance of that index and the clustering. Uh, so let's talk a little bit about table space flexibility and uh, you know the bad part of index in terms of inserts. So uh, DB2 can support a very high level of inserts. So a heavy insert it can do, and the reason is why that the insert in the to be inserted row does not have to go in a particular page of a table space. I mean, if the clustering index is there on the table, there will be a target page for that row, and it should be inserted in, in that order to best maintain the row clustering in the table. So, it's very easy for the table to find that row. Sometimes that target page is locked, and at times other processes are there, and that page could be full. So DB2 inserts the new row into some other page in that case. So that page could be physically very close to that page where it was intended to. Either sometimes it could be a very distant page, depending on availability. So the point here is that high inserts is always prioritized. So it doesn't stop, it doesn't stall the inserting process in the table space pages, and it will not be slowed down because of there is a contention on that page or because it is going to be full. So uh, table space page where it has to go, it will go. It is not that big of a problem. However, if you think about index, the story with the index is pretty different. So whenever a new entry is made, added in the index, whenever you insert, whenever there is an insert operation, there is a new key which gets inserted, the corresponding key into the index. The thing is, the new entry must go into the particular page because it has to maintain that ordering, and it has to maintain the physical ordering of the index entries. So there is no flexibility to place an entry elsewhere. So if the correct page is full, this is so when the correct page where it has to go is full, that is where the page splits triggers. And basically that operation involves moving a portion of the entries in the page to an empty page of the index, and the full page gets divided, and it stalls the whole process of insert. So that's the reason index place page splitting is problematic. It's an headache. It's a stress. We will discuss more about that. We will, okay, to make it interesting, I thought I will go to some fundamentals for those uh, for which this topic is new. There are questions. Okay. So let's, so the index structure in DB2 is basically a B tree or balance tree. And if you So why this balanced tree? It is it is because it is a very efficient way where you can search a particular row, or I mean find it. You can insert or delete, that rows of basically index keys in case of an index, while keeping the search path shorter and predictable. So it is a very efficient way, a very smart way of searching or inserting or deleting some rows from the table. If you see the hierarchy of pages, we call it nodes. At the top, there is something called as a root page, which is a single entry point, and it is at the top. In the middle, you will find non-leaf pages, which are the intermediate pages. And the direct traffic comes down into the tree via these non-leaf pages. So these non-leaf pages contain the key values, the keys from the index, as well as pointers to the next level pages. And then finally, you have a bottom layer of pages, which is called leaf pages, which basically contains a sorted index list and the pointers. When I say pointers in the leaf pages, they are basically row IDs, which are directly connecting to the page set of the data table space, actual data rows. And the leaf pages are linked as well sequentially. In addition to that, all leaf pages are at the same depth. So if you see the bottom layer of the leaf pages is equidistance from the top root page, based on the layering. The second thing is within each page, the keys are always kept in sorted order, ascending, descending, whatever. It will always be sorted. So these are some basic fundamentals. Let's go through quickly with an example to understand how the entries gets made into an index and how the splits happen at a very generic level. So what I'm going to talk about is an example. It's not actual DB2 page, 4K page, and the entries I'm talking about. This is very generic example, but it is analogous to what happens in DB2. So let's say we have set up this example where every leaf page can hold maximum of 3 index entries. And basically the entries are the index key value and the read list, or the RID. Each non-leaf page, including the root, when it's actually as a non-leaf, can hold max of 2 keys. So the non-leaf pages can hold maximum 2 keys and 3 pointers. Why 3 pointers? So 3 pointers are required because uh, there are 2 pointers needed for the keys and 1 pointer needed for the next level, pointing to the next non-leaf page or the leaf page. Right? So, but in the real DB2 systems, the whole capacity will depend on the index page size, which is the BP size, 4K, 8K, 16K, etc. And the length of the index key columns and the row ID size and the page overheads, it's typically much higher what we're talking here. So this is the first page, which is basically a root page or leaf page. The index uh, key is 50 and the row IDs are 1. So this is our first page got created. Now you insert a next key, which is 90, row IDs are 2. So it gets added in the sorted fashion. So first 50 is added, then next is 90. It is sorted. You insert another key, 30, row ID 3, it gets added. So, and the navigation start always from the root page. So now, as we discussed earlier, you can have maximum 3 keys in a root or leaf page. It is now full. Okay, so max 3 leaf entries are reached. So this is full now. Now the split happens when you try to insert another key. So try to insert 70 and R4 and the page is full. Now the split will happen. So what happens is the combined sorted keys, which are 30, 50, 70, and 90 in order, you can you I mean that you can divide these keys into half. So the 30, 50 in one group and 70, 90 in another group, and a new leaf page will be created. And then you can move the entries like 70 and 90 to one page, the new leaf page, and the 30 and 90, 30 and 50 to the original one. But another thing happens where you promote the keys to a new root page. So you take the first key from the new page, which is 70, and promote it upwards towards the parent level. So since the original page was the root page, we need a new level and a new root page is created, which is also non-leaf page. And the promote key 70 will be there into the new root page now, which is be uh, implicitly, which should be connecting or pointing to the new leaf page too. Whereas there is an implicit pointer with the older page where any keys less than 70 will be pointed to. So this is how you and the leaf pages will be connected. So this is how the first split happens and 2 layers are created. Now you further add values. You add 95. 95 gets added in the leaf page 2. Uh, 95 gets added into the leaf page 2, but now leaf page 2 is full. If you add something next, uh, a split will happen. Let's add 80. Now, if you add 80, 80 is more than 70, so it will go to the leaf page 20. Sorry, 2, leaf page 2 here, and it will be in sorted order. And page 2, as you seen last, it was full. It will get splitted. Now the combined keys will be splitted as well. 70, 80, 90, 95 in the order will be splitted. 70, 80, and 90, 95. A new leaf page 3 will be created where 90 and 95 will be added. This is all in ascending order. And the original leaf page 2 now holds 70 and 80. And there is an promotion of key as well. Now it changes to 90. Now you have two keys in the root page, which is 70 and 90. And there is an implicit pointer for the less than 70 values. So there are three keys now. It is full actually now. So this is how the addition happens. Now, just for the example purpose, I have shown. Now you further add values here. So what happens? The split keep on happening at the non-leaf pages, and the new root pages gets created every time. So this is the final stuff. Why I wanted to show you, that how actually page splits happen in a generic way, not very specific way to DB2. And the pages keep on adding. You get non-leaf pages. The levels get added in between root page and leaf page layers. So more page splits, more non-leaf page splits, enhances the height of the index hierarchy, and which is not good, because as the number of hierarchy levels go up, the traversal becomes stressful and not so good. So directly that page split is adding to the performance of your DML or DML activities like insert, delete, update, or select, all of them. So this is how it looks. So this is a basic concept behind how the index pages gets created and how the split happens. Now we'll go very um, specific case for the DB2 for ZOS. So index splitting in DB2 occurs when, as we have seen earlier as well, the same case, when you have to insert a new key to an already full index page. And in a B tree, the default structure is like the leaf page is at the level 0, and that contains keys and RIDs. So when a leaf page is full, on insert, DB2 allocates a new page from the free list. So whatever is available, or it extends uh, the pages, and then it will allocate. And then it redistributes the entries. So that is also happening. So first it is allocating a new page, then it is redistributing the data, right? And so when the leaf page splitting happening, uh, during an insert, as I said, a new page will be uh, allocated, and redistribution will be happening. So after redistribution, the new key, which was supposed to be inserted in that previous page, gets inserted in an appropriated page. So split happens in two ways. Basically, historically, it used to move, uh, you know, it used to divide by half, 50-50%. And half entries will be remaining on the old page, half will go to the new page, the number of keys. Then there is an asymmetric split. So what does asymmetric split mean is the engine detects a pattern, whether the keys are ascending or descending. So if the keys are ascending, then more entries will be left on the original page to accommodate future ascending keys. Whereas if it is the other way, the more entries will be moved to the new page. The goal here is to bring down the frequency of future splits. So that's how the asymmetric split happens. So during what happens when the split happens, the things which contribute, into the problems which is create is there are some structural changes happening. While doing that structural changes, uh, DB2 latches that entire index. It puts a temporary lock and acquires a p lock on that. And whenever this is one thing, another thing is it also creates a log record to document this operation. So two overheads are there. So if it is locking that particular page, nobody else can do anything during that time period. For the non-leaf pages, it is similar. That is also pull when a lower level page splits, the parent page undergoes a similar split. A new branch page is allocated. Pointer entries are distributed between the old and new branch pages. I mean the non-leaf pages. Similar process, but for the non-leaf pages. The splitting process can propagate upwards through the multiple levels and the index tree in the index tree, and the successive parent pages are also full. So the root page also gets filled, and then it gets it will be splitted, and the new root will be created, new leaf. So that's how organically the tree structure grows. For the root page split, if a split propagates all the way to the root page, the DB2 will create a new root page in that case, and it will increase the overall height, the number of levels of the index tree, and the root is typically 4K page size, and splitting it will create a new 4K root page above that previous level. But the good thing about index page splitting is that it preserves the physical ordering of the index key value. That is one of the good things. But there are negative impacts of the index page splitting, as we already discussed few of them, and we will discuss more in detail. So the split entries, which are there, which we just discussed about, which gets separated from the original page and gets moved to empty pages, which might be located far from the original page. So what it does, it disrupts the physical contiguity of the logically sequence of the pages. So there is one entry in the page number 4, and next entry is in page number 24. So there is a physical distance between that, and it's problematic. Why? Because the performance of index scans, basically the matching index scans, that degrades because of this. The distance between the pages are pretty high. So the physical jumps between these pages happens, and it degrades the performance drastically. That is one of the negative impacts of these splits. What you have to do is it requires an index reorg to be run so that you can just a minute. I think I have to connect my charger. Okay. Yeah, so you require an index reorg utility to run so that the physical pages are realigned in the sequence of the logical sequence. Yeah, serialization is one of the problems. What is serialization? So for the indexes on tables that are pretty high volume inserts are happening on those tables and indexes, the index space splitting can be a real drag because of the serialization. Because the page splitting process is serialized in DB2. What does that mean is that uh, when there is a process which needs, or a transaction or thread needs an access to that particular index page where the splitting is happening, it should wait for that split to complete the operation because it has a lock on it. And it is done, there is a reason, there is an intent behind it to make sure the data is integrated, the index data is, it is integrated over there. So the data integrity purposes, these split processes happen in a sequential order. And that's why it is serialized. But it impacts significantly, on the throughput. And it escalates further if you are doing it in a data sharing environment. So, but there is a catch that if index page splits generally, don't occur, or It doesn't happen for the indexes where the new values are higher than the existing values, sometimes, like for example, timestamps. So it doesn't mean that it will not happen, but uh, generally it doesn't happen for those type of keys. CPU IO overhead. So splitting a page requires, you have to copy entries from one page to another page. You have to latch and lock pages. You have to write logs. You have to create new index pages to the disk or to the GBP. So this whole process consumes a lot of CPU and IOs. And so this is very CPU consuming. It is an overhead, and the splits cause the synchronous log writes. So that is also an overhead. We discussed about latches. So when you have a latch or a so what it does is DB2 holds an index tree P lock on the affected page or pages, and in data sharing environments, this appears as a class 6 weights, and in non-data sharing is class 254. Uh, High split activity can cause a latch contention. So there will be another lock waiting for it, and there is a contention issue. That is an overhead. Insert throughput gets negatively impacted, as we already discussed. So frequent splits throttle insert throughput. Inserts into so if there is a key which tries to insert into the middle of the key range, which is called as non-monotonic keys. I mean, generally keys are either growing from low to high or high to low. But if it is in the middle, it can force many splits, and each split stalls the inserting transaction until the structure changes and the log writes complete. So in long term, if these splits are happening, repeated splits leave many pages only partially filled. Uh, in classical 50-50 split, one of the two pages will often be remained 50% empty, 50% full. Over time, the index consumes more pages, so you will be left with more pages. You will be left with more levels of pages, and obviously degrading the excess performance. Um, and buffer pools are also wasted because of that. So that is another problem. So heavy split leads to index. Yeah, so I mean, this is whatever we have discussed is whenever there is a heavy split, it is sort of, you have bloating in your stomach. So it is like bloating the index. So that's how we compare it. You need to reorg the index in those cases. What, what were the challenges? How do you diagnose these splits? Used to be really not so clear before DB213. You had a trace record, which was basically a performance trace class 4, which could monitor splits, called IFKIT 359. The problem with IFKIT 359 was it's a pretty high overhead in terms of CPU. Uh, And the problem is it generates a record for every split that is happening in whole DB2 subsystem, which is causing a performance issue itself on the system with frequent splits. So if the frequent splits are happening, it's a big overhead. Um, so because of these overheads and not so good, it's a performance trace class. It is not activated a lot of the times. And if you activate it, there is an CPU overhead, so you have to think about it. Also, it didn't the diagnostics which we get from IFKIT 359 are not full, and it doesn't carry like the unit of recovery ID or the thread, which is basically causing the split. It doesn't even tell you about the DB2's member ID from a data sharing group. So a couple of these information were not there, and it was very heavy to run these trace records. Another problem was The only thing which you had in catalog, basically in RTS, is index space stats, was the column reorg leaf var. So basically, uh, so there are two columns, reorg leaf near and reorg leaf var. So the reorg leaf near tells, the number tells that uh, after how many leaf pages you actually have that next page from the previous page due to all these splits and all that. So if it is within 2 to 16 pages range, it is called a near page, or uh, reorg leaf near is better. It's called a nearer page, I'd say that. And when it is more than 16 pages, in terms of the distance between the previous and the target, it is called a distant page. Ideally, the distance between two pages should be one page, actually. That is the best situation. But the value which you get from these RTS, it doesn't tell much. It will just tell you numbers in terms of how far, how nearer that page is. Um, this value can get incremented by other actions as well. It didn't indicate like how much time was being consumed by the potential splits. Overall, DBAs had a very fuzzy picture about it, and making it difficult to pinpoint the root cause and take effective corrective action. With DB213 brought some relief for us. So in DB213, IFKIT 396 was introduced, and it's a low overhead uh, to run this diagnostic because part of statistics class 3, and it was active by default. So and it also generates the records only for the splits, taking an unusually longer time. And unusually longer time means more than 1 second. So this focus on the most impactful splits without the overhead of tracing every single one. So you don't have to record everything what's happening. It also includes the URID, which was not there previously, and the DB2 member ID as well. So the benefit it makes the identifying process, driving long running and problematic splits much more straightforward. Another relief which we found in DB213 uh, is a couple of more columns. So with DB213, if you have DB2 catalog level V13R1501 and function level 500, you can get that. In sys index space stats RTS, there are three columns. One is called reorg total splits, which basically talks about the accurate count of all index space splits since the last reorg. Reorg split time, total time spent in milliseconds processing those splits, and reorg XX splits. That is the count of exceptionally long splits. And when we say that, the splits which takes more than 1 second. Uh, so these three very informative columns, which are very helpful. So with the improved tracing and the statistics, now DBS can clearly identify the process causing problematic splits and specific indexes. So you can now pinpoint. If you see if you query the catalog for a few indexes, this is just an view from catalog. You can get a better picture here. You- These are these were already there, like n levels, n pages, number of leaf pages, active leaf pages, get pages after last reorg. Now you have how many splits have happened from last reorg, also how much time it has taken in milliseconds, and how many exceptional splits which has happened. In mitigation strategy, uh, Colin, do we have time? Hello, Colin.
Yeah, we're doing quite well. We've got 10 minutes left by my reckoning.
Okay, okay. So on mitigation strategies, definitely you have to increase the index page size, basically buffer pools. So it's very straightforward. A larger page can hold more index entries and fewer splits in that case. Increase PCT free. We all know we have a certain percentage of space left on each page based on PCT free value. And there is a page which is left blank after a certain number of pages, which is a free page value. So if you leave some free space within an index space during the reorg to accommodate future inserts before needing a split, it is always good. Reorg frequently your indexes. This is a default. So generally the default value for free page is 0 and PCT free for index is 10%. And for table space, it is 5%. So these are some mitigation strategies. Some other strategies might include try to minimize the index key length, because index keys are, if they're shorter, they are practical, and more entries can be accommodated on one page if they are smaller. So when you create the keys, it should be created very intelligently so that you do not fill the index pages pretty easily. Index compression, yes, compressing the index is good. It will bring down the usage of the space, but it has its own performance issues associated with the compression, and you have to maintain it. So it's good and bad both. You have to take a call. The typical answer a DBA gives, whenever you have confusion, it depends. So whether you have to on the index compression or not, it depends on your shop and how you want to pursue that. If the splits are causing some IO stalls, and ensure that the buffer pools are suitably sized and tuned, and GBPs have real storage and stuff over there. So make your buffer pool tuning strategy and work on it. It will help in that. You might have heard about the fast traversal block or fast index traversals, FTBs. So use it. Those are good, makes the performance of the DML activity faster. So these are from few mitigation strategies. I have provided some links which you can always click on to. I'm sure you must be going through all of these IBM links which are there, very helpful. Okay, so I think I'm done with my monologue. So if you have any queries or not even queries, if you have to add anything, or if you have some information which you want to add here, for the benefit of the group, you are all welcome. Please do that.
Yeah, if you've got any questions, please put them in the chat and I can unmute you, or however you want to play it. If there's any questions, please shout now. Right, it's very quiet out there. It's early in the morning for some people.
You need coffee.
Yes. So nope, there's nothing at the moment. But thanks very much, Sarab. This is session 9G, I think.
Yep.
Yes. So please do provide feedback so that we can make changes, etc., for further conferences. I hope you've enjoyed that as much as I did. And the next session is at 11:15, when Mark Wader is going to be looking at some data sharing issues. So hope you join us then. Otherwise, thanks very much for your attendance, and do provide your feedback. Thanks, Sarab. That was great.
Thanks, Colin. Thanks, everyone. Have a nice day.